Okay, in this lesson, we are going to discuss about the impulse and momentum. This is the final chapter in rigid body dynamics in this course. So let's take a look at the impulse and momentum. Before we go into impulse and momentum, let's do a bit of recap. Previously, we have learned about the principle of work and energy. From the principle of work and energy, it states that the initial kinetic energy plus the total work done to move from position 1 to position 2 is equal to the final kinetic energy. Now, the kinetic energy can be translational and can be rotational, or can also have both translational and rotational terms. This is what we have covered in the principle of work and energy. The same principle also applies for impulse and momentum. In impulse and momentum, we have basically three equations. The first two equations indicates the principle of linear impulse and momentum. This has been divided into x-axis and also y-axis. Because we are currently talking about planar kinetics, therefore we only have the motion in two axes, which is x and y axis. We are not going to have a motion in z axis because this is not a three-dimensional problems or three-dimensional motion. We are only talking about planar motion. So what this equation states is that it states the initial linear momentum either in x or y axis. So initial linear momentum that is represented by mv1 plus the linear impulse. This integration of f dt is basically the impulse, is equal to the final linear momentum mv2. So this is pretty much similar to the principle of work and energy. Previously, we have initial kinetic energy here plus the total work done equal to final kinetic energy. For this chapter, impulse and momentum, we have initial momentum plus the total impulse equal to the final momentum. So these two equations represent the linear impulse and momentum. The third equation represents the principle of angular impulse and momentum. So the first term here is the initial angular momentum. This term here is the angular impulse, integration of moment about g dt equal to the final angular momentum. Now let's take a look at the linear and angular momentum. Linear momentum is given by or is denoted by symbol L, that is equal to the mass times velocity. So L equals to mv. Vg can be divided into x or y axis like what have been shown in the previous slide. So this is the linear momentum. Now the angular momentum is calculated about an axis. So let's say now we are calculating about an axis passing through G, the center of gravity. So we write this as hg. The angular momentum is represented by symbol h. Now hg is equal to the mass moment of inertia about g, ig, times the angular velocity omega. So the angular momentum is equal to I times omega. Now this is the angular momentum calculated about the center of gravity. Now let's say we want to calculate the angular momentum about other points other than the center of gravity. Let's say point P here. So the equations become HP now about point P is equal to IG omega plus another two extra terms. This is identical to the kinetic moments about point P. This equation here, you can refer to the force and acceleration chapter where we talk about kinetic moments about point P, this is pretty much the same. Instead of alpha here, we have omega now, Ig omega, plus mvgx, here mvgx in x-axis, multiply with the distance of dy here to go to point P, and mvgy in y-axis, this one multiply with dx, this is dx, and this is positive counterclockwise. So basically this is wrong, this should be negative here. mvgx is going to point P in clockwise direction, so this should be negative. mvgy is going in this direction, in counterclockwise direction, so this should be positive. So this should be positive here, and this here should be negative. Okay, because now mvgy is going to point P in counterclockwise direction. Sorry, mvgx is going to point P in clockwise direction, and mvgy is going to P in counterclockwise direction. So this will be positive. This here is positive, and this one here is negative. Now, from previous chapter, we know that a rigid body can undergo three types of motion. There is translational motion. So if the rigid body is undergoing translation only, then the linear momentum is equal to mv, and since there is no rotation of the body, therefore the angular momentum is equal to 0. This is for the case of translation. If the rigid body is having rotation about a fixed axis, of course point G still have a translation, so L linear momentum is still equal to mvg, and the angular momentum about hg is equal to ig omega. Now we can also calculate h about point O. Therefore, if we calculate HO, this will be equal to IO omega. Now IO is the mass moment of inertia about point O, which can be calculated using the parallel axis theorem. This is the parallel axis theorem. IO is equal to IG plus MD square. D in this case is the distance between point G to point O, which is represented by RG in this particular case. So for a general plane motion, we have also both terms, linear momentum equals to mv, and also angular momentum equals to ig omega. And if we are able to find the location of IC, then this can be written as HIC, or angular momentum about IC, that is equal to IIC omega, where IIC can also be calculated using the parallel axis theorem, similar to what we have here. Okay, that is the linear and angular momentum. Remember, in the equation of principle of impulse and momentum, we also have impulse. Now let's talk about impulse. Let's see this example here. Now we have a cable that is being pulled by a force P, and we need to determine the angular velocity of this spool in 5 seconds. This is the keyword here. Whenever you see time is given, then this is definitely an impulse and momentum question. So how do we proceed? To calculate the impulse, we need to draw the free body diagram. So please remember, every time you face this impulse and momentum question, please draw the free body diagram. So this is the free body diagram of this rigid body here. We have the weight pointing down, we have the normal at point A, we have the friction force, and also the force P. So here as you have already seen that we have three equations. So the first one is we need to calculate what is the linear impulse in x-axis. So let's take a look at the forces. We have two forces in x-axis. One is force P that is pointing in positive direction of x-axis, and the friction force that is pointing in the negative direction. So remember, impulse is force times time. So we have two linear impulse in x-axis, P, the force P times T, T here being 5 seconds, and also the force, the friction force in negative direction. So minus Fa times T. And also linear impulse in y-axis, we have two forces in y-axis. One is the normal force pointing in positive direction, so we have Na times T. T is 5 seconds in this case. And we have the weight that is pointing down in negative direction, so minus weight times T. So these are the impulse, linear impulse in y-axis. These are linear impulse in x-axis. Now the third equation requires us to calculate the angular impulse. Now let's say we calculate the angular impulse about point G, about the center of gravity. So the weight and also the normal force does not have any moment about point G. Therefore, there is no angular impulse about point G for these two forces. Now we only have the friction force Fa and we have the force P. So Fa, to make it a moment, we have to multiply with the distance. Remember, moment is force times distance. Now we have Fa times the distance from this to point G, that is 0.75. So Fa times 0.75 becomes a moment. To make it angular impulse, moment has to be multiplied with time. So we'll multiply again with T. T here being 5 seconds. For force P, P is multiplied with the distance to point G, that is 0.4. So P times 0.4, we get a moment of P, and then to make it angular impulse, we multiply with time. So P times 0.4 times T. Both of the forces have positive moments, because now we calculate the moment positive in clockwise direction, okay, according to this rotation. And we have point P going to G is in clockwise, and the force Fa going to G is also in clockwise direction. Therefore, both forces have positive angular impulse about point G. Next, let's take a look at the conservation of momentum. Let's say in some cases that if there is no or negligible net external linear impulse, then the impulse is then equals to 0. So we are left with the initial momentum that is equal to the final momentum. And this equation is known as the conservation of linear momentum. We can also have a conservation of angular momentum where the angular impulse is negligible. So we will have the equation of initial angular momentum is equal to final angular momentum. So these are known as the conservation of momentum. Now let's take a look at an example of a hammer hitting a nail. So it may be possible to apply conservation of linear momentum because we have a non-impulsive force, that is the weight here, because it acts over a very short period of time. So let's draw a free body diagram. If we separate these two objects and draw the forces, that is the forces being applied by the hammer on the nail, and of course the nail will also apply the same force in opposite direction to the hammer. And then we will have the weight of the hammer and also the weight of the nail. So the weight of hammer and nail are small relative to the force F here, and that is why the weight in this case is the non-impulsive force. So there is no impulse or negligible impulse by this weight. And since the impact duration is very short, we consider that this weight as non-impulsive. And then if we draw the free body diagram together now, the internal forces F just now will cancel out each other. And since the weights are non-impulsive, therefore we can say that in this case the linear momentum is conserved, and the angular momentum can be conserved while the linear momentum is not. So it is not necessary that both linear and angular momentums are conserved at the same time. And such cases occur whenever the external forces creating linear impulse pass through either the center of mass of the body or a fixed axis rotation. So to relate the conservation of momentum, we go into the last topic of this chapter, that is the impact. Now let's do a recap on particle dynamics. Currently we are talking about rigid body dynamics, but in particle dynamics there are two types of impact. The first one is known as central impact, where the line of impact is on the same line as the velocity of the particles. And we also have oblique impact, where the velocity is coming at an angle of the line of impact. And in rigid body dynamics, we have an impact that is the line of impact is not passing through the center of gravity. For example, the center of gravity of object A might be somewhere over here. The center of gravity of object B might be somewhere here. So the line of impact does not pass through the center of gravity of these two objects, and this is known as eccentric impact. So eccentric impact occurs when the line connecting the mass center of two bodies does not coincide with the line of impact. Often occurs when one or both of bodies are constrained to rotate about a fixed axis. So one body is rotating and it is spin connected at point O. Rigid body A is impacting the rigid body B. So in general, when we have the eccentric impact problem, we will have another equation that is known as the coefficient of restitution, which is denoted by symbol E. Coefficient of restitution states that the final velocity of object B minus the final velocity of object A is divided by the initial velocity of object A minus the initial velocity of object B. So this is the coefficient of restitution, and this equation might be needed in order to solve the problem that is involving impact in this chapter of impulse and momentum.